In this video, we're going to look at triple integrals as volumes. We can use triple integrals to find volumes of solid objects. Volumes of basic geometric solids can be easily computed using formulas that already exist in many of the geometry and algebra books you've already seen. But if you've ever wondered where on earth they came up with these formulas, you're about to find out. You're also going to learn how to find the volumes of a much wider variety of solid objects than the standard geometric solids that you might already be familiar with. So here's an example. I want to find the volume of the solid for the region in the first octant that is formed when the cylinder z is equal to sine of y, for 0 is less than or equal to y, which is less than or equal to pi, is sliced by the planes y is equal to x and x is equal to 0. It's often useful to see if we can make a quick sketch first in order to help us visualize what our integration has to look like. So I've done a quick sketch of what this is going to look like, and you'll notice that it's a dome-shaped wedge in the first octant, which has one side that aligns with the YZ plane, the bottom side aligns in the XY plane, and the front side aligns in a plane defined by the equation y is equal to x. You'll notice that I have a vertex at the origin 0, 0, 0, another vertex at pi, pi 0, and another vertex at 0, pi 0. So I can write my triple integral as the triple integral over the region D dv, with the region D being the set of all points x, y, z, such that 0 is less than or equal to x, which is less than or equal to pi, x is less than or equal to y, which is less than or equal to pi, and 0 is less than or equal to z, which is less than or equal to the sine of y. And I've simply looked at my sketch to pick these limits of integration out. Now I'm going to write my triple integral as an iterated integral. My volume is going to be given by the integral from 0 to pi of the integral from x to pi of the integral from 0 to sine y dz dy dx. I'll integrate the innermost integral, the integral from 0 to sine y dz, which is equal to z evaluated from 0 to sine y, and that becomes just sine y. Notice by picking this as my first integral, I'm able to immediately eliminate the z variable and reduce myself to a double integral over x and y. I'm going to plug sine y in as the integrand to my middle integral. This gives me the integral from x to pi of sine y dy. This becomes negative cosine y evaluated from x to pi. This gives me cosine x plus 1. This becomes the integrand in my outer integral, and I evaluate the integral from 0 to pi of the quantity cosine x plus 1 dx. This becomes sine x plus x evaluated from 0 to pi, and it gives me pi. This is the volume for this particular region. Let's work another example. I want to find the volume of the solid for a wedge of a cylinder described by x squared plus 4y squared is equal to 4 that lies between the planes z is equal to 3 minus x and z is equal to x minus 3. Again, I want to sketch the region so I have a good idea of what it is I'm looking at. I'm looking for the volume in this area of my cylinder bounded by these two planes and the cylinder itself. The region of integration in the xy plane is an ellipse. The limits of integration on x are from -2 to 2. The limits of integration on y are from -1/2 times the square root of 4 minus x squared to 1/2 times the square root of 4 minus x squared. And the limits of integration on z are from x minus 3 to 3 minus x. I want to integrate first with respect to z, and then I want to integrate with respect to y, and finally I will integrate with respect to x. So my volume V is given by the integral from -2 to 2 of the integral from -1/2 times the square root of 4 minus x squared to 1/2 times the square root of 4 minus x squared of the integral from x minus 3 to 3 minus x of dz dy dx. I'm going to work on the inner integral first and take the integral from x minus 3 to 3 minus x of dz, which is equal to z evaluated from x minus 3 to 3 minus x. This is equal to 6 minus 2x, which becomes the integrand in my middle integral. This is the integral from -1/2 times the square root of 4 minus x squared to 1/2 times the square root of 4 minus x squared of the quantity 6 minus 2x dy. I do the integration and I get the quantity 6 minus 2x times y evaluated from -1/2 times the square root of 4 minus x squared to 1/2 times the square root of 4 minus x squared. I plug those limits of integration in. I get 6 times the square root of 4 minus x squared minus 2x times the square root of 4 minus x squared. This will become my integrand in my outer integral. So I'm going to set up the integral from -2 to 2 of the quantity 6 times the square root of 4 minus x squared minus 2x times the square root of 4 minus x squared dx. I'm going to integrate it term by term, and I get 3x times the square root of 4 minus x squared plus 12 times the inverse sine of x over 2 plus 2/3 times the square root of 4 minus x squared, evaluated from -2 to 2. I plug in those limits of integration and I get 12 times the inverse sine of 1 minus the inverse sine of -1, and that is equal to 12 pi for the area of my wedge in my cylinder. Let's work another example where I want to evaluate the following integrals. I want to evaluate the integral from 0 to 1 of the integral from y to 2 minus y of the integral from 0 to 2 minus x minus y of xy dz dx dy. And I want to evaluate the integral from 1 to 6 of the integral from 0 to 4 minus 2y over 3 of the integral from 0 to 12 minus 2y minus 3z of 1 over y dx dz dy. In both cases here, I am not working with a volume because I have a function that does not equal 1 inside my integrand. In these cases, my function inside my integrand represents a density. So when I compute these triple integrals, I'm going to get the mass of my object. For the first one, I'm going to evaluate the integral to get the mass of an object with density xy. That integral is the integral from 0 to 1 of the integral from y to 2 minus y of the integral from 0 to 2 minus x minus y of xy dz dx dy. I evaluate the inside integral first. This is the integral from 0 to 2 minus x minus y of xy dz. This gives me xyz evaluated from 0 to 2 minus x minus y. This gives me xy times the quantity 2 minus x minus y, and I can distribute that xy and get 2xy minus x squared y minus xy squared. This becomes the integrand in my middle integral, the integral from y to 2 minus y of the quantity 2xy minus x squared y minus xy squared dx. I do the integration term by term. I get x squared y minus 1/3 x cubed y minus 1/2 x squared y squared evaluated from y to 2 minus y. This gives me 4/3 y minus 2y squared plus 2/3 y to the 4th. This is the integrand for my outer integral, the integral from 0 to 1 of the quantity 4/3 y minus 2y squared plus 2/3 y to the 4th dy. Integrating term by term gives me 2/3 y squared minus 2/3 y cubed plus 2/15 y to the 5th evaluated from 0 to 1. I plug in the limits of integration. I get 2/3 minus 2/3 plus 2/15, or 2/15 is the mass of my object. Now I want to evaluate the mass given by the integral from 1 to 6 of the integral from 0 to 4 minus 2y over 3 of the integral from 0 to 12 minus 2y minus 3z of 1 over y dx dz dy. My innermost integral is the integral from 0 to 12 minus 2y minus 3z of 1 over y dx. This gives me x over y evaluated from 0 to 12 minus 2y minus 3z. This gives me 12 minus 2y minus 3z all divided by y. I'm going to write this a little bit differently in my integrand for my middle integral. I'm going to write the integral from 0 to 4 minus 2y over 3 of 1 over y times the quantity 12 minus 2y minus 3z dz. I do that integration piece by piece, and I get 1 over y times the quantity 12z minus 2yz minus 3 halves z squared, all evaluated from 0 to 4 minus 2y over 3. I plug in the limits of integration and do quite a bit of algebra and simplification. And I get 1 over y times the quantity 24 minus 8y plus 2/3 y squared. This becomes the integrand in my outer integral, the integral from 1 to 6 of 1 over y times the quantity 24 minus 8y plus 2/3 y squared dy. I'm going to integrate this term by term. I get the integral from 1 to 6 of 24 over y dy minus 8 times the integral from 1 to 6 of dy plus 2/3 of the integral from 1 to 6 of y dy. This gives me 24 times the natural log of the absolute value of y minus 8y plus 1/3 y squared, all evaluated from 1 to 6. I plug in those limits of integration and do some simplification, and I get 24 times the natural log of 6 minus 85 over 3. Now you get to try it. Pause the video and find the volume of the solid described below using triple integration. When you're ready, restart the video to check your understanding. You want to find the volume for the region in the first octant bounded by the cone z is equal to 1 minus the square root of x squared plus y squared, and the plane x plus y plus z is equal to 1. It's going to help to construct a sketch of what this region looks like. I get a portion of a cone in the first octant that has a peak on the z-axis at z equal 1 and is sliced by a slanted plane given by x plus y plus z is equal to 1 and bounded on the bottom by the xy plane. I want to examine this region in the xy plane a little bit more closely to help me determine my limits of integration. So I notice that the plane and the cone cut off the arc of a circle where the line and curve intersect at y is equal to 1 on the y-axis and x is equal to 1 on the x-axis. When I look at this, I can see that my x values in the xy plane extend from the plane of the slanted line to the curve of my cylinder, so that I go from x is equal to 1 minus y minus z to x is equal to the square root of 1 minus z quantity squared minus y squared. My y values will go from 0 to my curve. This means they go from 0 to the curve y is equal to 1 minus z. My greatest value for z will be 1, and this is when x is 0 and y is 0, so that z goes from 0 to 1. So this gives me my 3 limits of integration. I'm going to set up my iterated integral. I'm going to take the integral from 0 to 1 of the integral from 0 to 1 minus z of the integral from 1 minus y minus z to the square root of 1 minus z squared minus y squared dx dy dz. The innermost integral is the integral from 1 minus y minus z to the square root of 1 minus z quantity squared minus y squared dx. When I do this integration piece, I get the square root of 1 minus z quantity squared minus y squared minus the quantity 1 minus y minus z. This is the integrand that will be used now in my middle integral. My middle integral becomes the integral from 0 to 1 minus z of the square root of 1 minus z quantity squared minus y squared dy plus the integral from 0 to 1 minus z of the quantity y plus z minus 1 dy. I'm going to let a equal 1 minus z in the first integral here because it makes it easier to see what I'm doing. So I get the integral from 0 to 1 minus z of the square root of a squared minus y squared dy plus the integral from 0 to 1 minus z of the quantity 1 plus z minus 1 dy. This gives me y over a times the square root of a squared minus y squared plus a squared over 2 times the inverse sine of y over a plus y squared over 2 plus yz minus y, all evaluated from 0 to 1 minus z. I have to plug the value 1 minus z back in for a here. And when I do that, I get a really long involved expression. But notice that I'm going to have things drop out that go to 0. I end up with pi times 1 minus z quantity squared over 4 plus negative z squared plus 2z minus 1 all over 2. This becomes my integrand in my final integral. My outer integral is given by the integral from 0 to 1 of pi times 1 minus z quantity squared over 4 plus negative z squared plus 2z minus 1 divided by 2. So I integrate term by term. I have the integral from 0 to 1 of pi times 1 minus z quantity squared over 4 plus the integral from 0 to 1 of negative z squared plus 2z minus 1 over 2 dz. I integrate that and I get another long expression that I plug my limits of integration into, and I get pi over 12 minus 1 over 6. Be sure and let me know if you have any questions about finding volumes or masses using triple integrals.